Hello and welcome. In this video, we'll be exploring ReadWriteMany storage on Google's Kubernetes Engine service. ReadWriteMany storage allows multiple pods to access the same persistent volume simultaneously. These pods can not only read from the same persistent volume, but also write to it. Think of it as a network storage system that's both performant and platform agnostic, yet easy to use. Today, we'll demonstrate this using Google Kubernetes Engine, or GKE, as our use case. We'll have our GKE cluster connect to different storage backends to support read-write-many storage. Filestore, Google's managed NFS server, is an obvious choice, but other options like NetApp are also available. Let's get started by creating a new cluster in the Kubernetes Engine service. We'll choose a standard cluster for more control over the setup and pick a zonal setup in US Central 1. To reduce costs, we'll lower the node count and adjust the node types. For our purposes, we'll select an E2 Standard 2 machine, which provides 2 virtual cores and 8 GB of memory. Most of the other defaults can remain unchanged. However, it's crucial to go to the Features page and enable the Filestore CSI driver. CSI drivers allow Kubernetes to natively use different storage backends while keeping our YAML configurations and Kubernetes primitives straightforward. While other options like cloud storage exist, we'll focus on Filestore for our read-write-many volumes. Let's click Create to proceed. Next, we'll use the Cloud Shell editor to deploy an example resource to our cluster and set up our read-write-many system. We'll obtain the necessary YAML configurations from the Filestore documentation to get started. We've already set up the Filestore CSI driver, and most of the rest is automated. However, we need to enable the Cloud Filestore API. Let's do that quickly while our Cloud Shell editor opens in a new window. Simply search for Filestore in the top search bar and click Enable for the service. Once we've got our workspace set up in the IDE, it's time to create a YAML file for our Filestore-backed read-write-many use case. Let's grab some code directly from the documentation. Whether we access an existing Filestore instance or provision one dynamically, the principles are virtually the same. Let's opt for the dynamic approach. We'll start by specifying our persistent volume claim with the read-write-many access mode. Next, we'll authenticate with our Kubernetes cluster to see which storage classes are available. To do that, we'll set our project and authenticate with the cluster. Now that we've retrieved our storage classes, we see several options provided by the Filestore CSI driver. Let's choose the zonal option for our storage class name. 1 terabyte should suffice. That's actually the minimum file store instance size. Next, we'll create a deployment that uses this volume. Notice that we're using the pod PVC specification as a mount for the HTML folder on our Nginx web server. We're also deploying 3 replicas to demonstrate reading and writing from multiple pods. Let's apply this configuration to the default namespace. It may take a few moments for the pods to provision because our Filestore instance needs to start up, but don't worry, the Filestore CSI driver handles the provisioning automatically. Once we receive the notification that the Filestore instance is ready, our Nginx web servers should be up and running shortly thereafter. To really showcase the ReadWriteMany concept, let's log into a couple of these pods. We'll run a bash shell and navigate to where our ReadWriteMany storage is mounted. As expected, there's nothing there yet. Let's access another pod as well. Now, if I create a file on the first pod, then on the second pod, we navigate to the shared NFS directory and see that same file and even update it. Back on the original pod, we'll see that update reflected. This demonstrates how we can share data across multiple pods using ReadWriteMany storage. The NFS option is simple and easy to set up, with Google managing everything for us. But what if you need another option? As a bonus, let's explore NetApp Volumes. We'll navigate to that page in our existing Google Cloud project and enable the API. Since it's consumption-based pricing, there are no licensing or upfront costs to worry about. To integrate NetApp Volumes with our Kubernetes instance, we'll need the Trident system from NetApp. This is a CSI driver, the container storage interface, that enables our Kubernetes cluster to access and utilize NetApp storage efficiently. We'll navigate to the Deploy folder and look into the CRDs. Here, we'll find the Trident Orchestrator CRD, which we'll use to set up our Trident Orchestrator. This will handle our volume management. For the specific CRD, let's grab the Trident Orchestrator CRD under the Trident NetApp IO API group. We can confirm that the group is correct and click to get the raw file to apply to our Kubernetes cluster. So let's exit our earlier testing of the ReadWriteMany storage on Filestore and apply that CRD file using a kubectl apply command. We can see that the CRD was created successfully. Next, we need to deploy the operator itself. Let's go back into the repository and use the bundle. In this bundle, we've got resources like a service account, a cluster role, and other components that the operator requires to function, in addition to the operator deployment itself. Once again, grab the raw file and deploy it. It seems the deployment requires a namespace, so we'll create one named Trident and reapply the file. Let's use a kubectl command to verify that everything is running properly. We're encountering an issue with the pod. Why is our pod failing to start? We might be ahead of the curve with this container version. Let's check Docker Hub to see if this is a pre-release container. Searching for version 25.0, we see that only 25.02 has been pushed so far. Let's switch to this previous version. Version 25.02 looks stable. We'll grab the deployment file for that version, and of course, we need the raw file to apply. There are a few small changes, and we want to ensure that the pod starts up cleanly. And there it is. It came up quickly, so we can proceed to the next steps. Next, we need to install the container resource. This is another file from GitHub located in the CRD directory. We'll use the CR file, the main one. Let's grab the raw file and deploy it. As we deploy, we see a daemon set starting up. This is our Trident, which runs on each node. We also have a controller pod that should come up. Notice that these pods have several sidecars. In fact, the controller has 6 containers running in that pod. We'll wait until everything is ready before proceeding. It looks like we had a pod restart while spinning up the daemon set on each node. Let's ensure everything settles cleanly. We'll let this run for a minute or two to confirm stability. All right, that looks good. Now, let's set up our storage pools and volumes. A storage pool specifies capacity, service level, networking, and security configurations. We'll use the Flex setup with zonal availability co-located with our cluster, and note that there's a minimum capacity of 1 terabyte. We'll set this up in our default network. Now we receive a message indicating that private services access isn't set up in our Google Cloud project. What's causing this error? We need to configure that to avoid any failures. Let's open Google Cloud in a new tab, navigate to VPC Networks, and set it up in our default VPC. This setting is found under Private Services Access, which is a bit buried in the VPC configuration. We'll need to enable the API and allocate an IP range. We'll let Google automatically create a range for us, and we'll assign it a name. Just like that, we have private services access and can continue setting up our NetApp system. We'll skip Active Directory configuration and won't customize the encryption setup for this storage pool. Now the fun part. Let's click Create. It seems the system didn't like that we didn't have Private Service Connect configured initially. Have you ever forgotten to set up a prerequisite step? It happens to the best of us. Let's try again now that we've set it up. Click to set up the connection and create. This looks better, and I expect we'll be able to submit the storage pool specification properly now. Indeed, we're able to submit it, and the capacity is spinning up. What we're waiting for is the ready status, indicating that our storage pool is good to go. Our Kubernetes Trident system will handle creating volumes in that storage pool, so we don't need to do that ourselves. This specification looks solid and will start accumulating volumes in no time. A prerequisite for this setup on the Kubernetes side is having a service account for this connection, specifically one that has access to create and delete volumes in our NetApp setup. So let's apply that role at the project level. We'll search for NetApp and select NetApp Cloud Volumes Admin. That's all we need. Click Done, then generate a service account key for this account. Go in, generate the key, and save it locally. Next, we need to integrate this service account into our YAML specifications. One option is updating the Trident orchestrator we deployed earlier. Let's grab the code and update it to better work with our GCP-centric setup. In the Trident orchestrator configuration, we'll provide the cloud provider field set to GCP and specify our service account. Let's grab that service account email from our Cloud IAM page and use it in our specification. Then apply that to our cluster as an update. We'll also create a Trident backend configuration. This is just a placeholder. We'll adjust things like the correct project number and location. The name of our storage pool is needed here too, so let's grab that from the console. It looks like we named it Demonstration. Let's give this a try, apply the backend, and see if we run into any issues. Wait, we're not getting any status. Something's off. I think I know what's wrong. We need to adjust our namespace to match the one used by our other Trident components. Let's delete the Trident backend configuration and recreate it in the proper namespace. There we go. Now we have a status, although it's showing as failed. The error message points to an issue finding our storage pool in the specified region. Maybe it's not accepting the zone specification in our location configuration. Let's adjust that and see if it helps. Still no luck. I suspect the authentication isn't working as expected. Let's check if workload identity is enabled on our Kubernetes cluster. Ah, it's disabled. No wonder we're not getting the authentication integration we need. Enabling workload identity should fix our setup. Let's verify which service account our controller is using. It's called controller in the Trident namespace. Traditionally, we'd bridge the Google Cloud Service account and the Kubernetes Service account with two commands, but I suspect we can enable this with a single command using the latest workload identity system. We'll create a project IAM binding using our Trident controller service account in the Trident namespace as the principal. Let's double check the role for our service account. We used NetApp Cloud Volumes admin, and here's the role ID. All right, let's give it a try. Looks promising. Since we used the simplified method, we can delete the old service account. We included it earlier in case you needed to use traditional authentication methods. Back in our IDE, let's check our Trident backend configuration. Our last attempt was a few minutes ago. To speed things up, let's delete the backend and recreate it. Since we're still getting a failure on our cluster, let's check one more prerequisite. We need to ensure that the GKE metadata server is enabled. Specifically, that's a setting at the node pool level. So let's take a look at our node pool. Oh, it turns out we had it disabled. Let's edit our node pool to enable the GKE metadata server. We'll wait briefly for the node pool to update. Do you think this last change will solve our issue? Let's recreate our backend and find out. To be thorough, let's refresh all our pods in the Trident pool to ensure they're picking up the new configurations. Since these are part of daemon sets and other managed pod constructs, they should come back up automatically and easily. With all our pods healthy, let's try our Trident backend again. If we're still facing issues, perhaps it's because of that attempted shortcut with the workload identity and permissions. Let's recreate our old service account and use the more traditional approach for workload identity. We'll name it Demonstration and assign the NetApp admin role. Next, we'll run the 2 commands to establish the identity bridge. First, we'll add an IAM policy binding to our service account. Grab the ID and assign the IAM workload identity user role. For the member, we'll set it to our Kubernetes service account. Then we'll set an annotation on the Kubernetes side to complete the bridge. And finally, we've got it. Our backend is created. After a few configuration tweaks, we've overcome the issue. Now comes the fun part. We can start creating our volumes. Let's check our storage classes first. So far, nothing is being provided by the Trident system. Let's go ahead and create a storage class. Here's our storage class using the Trident provisioner. Let's apply it. The big test now is using a persistent volume claim. We'll copy our Filestore example, label it as NetApp, and make a couple of tweaks. Importantly, we'll specify the storage class we just created, NetApp Volumes NFS. Let's apply that and see if everything goes smoothly. The critical part is the persistent volume, and it looks like the provisioning is successful. Our server is up and running. Let's check our volumes in the NetApp space, and there it is, our Flex Volume Terabyte NFS instance. Let's log into a couple of pods as we did before to test our setup. And just as we anticipated, it comes up on our other pod, and we can even make edits to it. This proves that our NetApp ReadWriteMany storage is working correctly, just like our Filestore example from earlier. If you'd like to support the channel, consider starting a free trial of our new design tool, which is linked in the description, and let us know what you think. We'll include all code and the diagram file in the description as well. If you have any questions, please post them in the comment section and we'll do our best to respond. Thank you very much for watching till the end, and please enjoy responsibly.